Welcome to part 9 of our Fastenation series. Today's topic is going to be focused on sheet metal screws. So what we have laid out on the table today is a combination of a range of examples of different types of sheet metal screws, the drive systems that are used for installing them, and I've also included some of the tools that will be used for preparing the materials for applying these fasteners. So some of what we're going to cover today will include developing an understanding of the anatomical characteristics of these particular screws and how those are useful for specific applications, and we're also going to want to look at some of the drive systems for both their function and for the aesthetic properties that they have. So let's get into just looking at categorizing the four general types of what we call tapping screws. So tapping screws are sheet metal, thread forming, thread cutting, and self-drilling. So sheet metal screws are probably the most common, and here we see 5 examples on the table here and their associated drives. The characteristics of a sheet metal screw is that it has a pointed end, it has widely spaced holes, and it typically requires us to drill holes in advance or to pilot a hole in advance of driving those screws, except with the thinnest of materials. Thread forming screws, like we have here, are characterized by a blunt point on the end, and they can be used to form threads in metal, plastics, and plywood. Thread cutting are screws that are blunt and tapered, and I don't have a really good example on the table here to share with you, but those characteristics are a blunt end, a tapered screw, and it has this tapping end that have flutes like a drill bit for ejecting the material as it cuts the thread in. And those can be used on everything from metal to plastic to plies. And last but not least, we have some examples of what are called self-drilling, self-tapping screws. And those are most typically used for fastening sheet metal, where you're doing things like attaching metal paneling to the side of a structure like a pole barn. So remember, the hole sizes that we need to create in the material, the pilot holes, vary according to the thickness of the material we're working with, and you can find reference charts online, or McMaster-Carr is a good source for a reference choice, or a place where you can reference the different choices when selecting, to select not just the appropriate fastener, but to know what size hole you have to drill in advance of that. And you see that almost all of these sheet metal screws have what we call a pan head, like we see here, or here, or a what's called a truss head, which is a wide head screw, or a combination of a head and a flange or a washer. And this is all about distributing the load over more surface area so it has a better hold. And remember, the softer the material is that we are making our attachment to that metal with, the more load distribution we want to have. So we're going to, I have a couple of setups here. One is a setup to drill through 2x2 square tubing with a 16 gauge, or approximately a 1/16 of an inch thick wall. I have another setup where I'm doing an attachment of felt around a piece of copper, and I think we're also going to give a go to taking some sheet metal that I recycled from a peanut can. Metal cans are a great source of inexpensive thin gauge sheet metal. So we're going to look a little bit about, at trying to install some fasteners in that, and trying to do some other simple bending processes and punching processes with that. So those of you that saw the drilling and driving module that we did a couple weeks ago know that whenever we're going into metal, we always need to use a center punch to mark the location of where we want that hole to be. Whether that means that you're drilling with a drill bit or using a self-drilling, self-tapping screw. So the beauty of these spring-loaded center punches is that I can vary the amount of tension or how hard it punches in the material, so that when I'm working with really delicate thin gauge material, like the material that I repurposed from this peanut can, that it's not going to grossly deform or bend the material when I make that punch or dimple, which serves as a reference point for that drill bit to follow. So we're always going to punch in advance of drilling. When we're working with cross sections that are an 1/8 inch or thicker, we're most typically going to be using a drill bit. When we're working with cross sections that are 16 gauge and thinner, we're commonly going to use a step bit like I have here, and or a hand punch like this. And again, remember, the reason that we need to move away from twist bits, especially when we start to bore larger diameter holes, is because the material being so thin is that it has a tendency to grab in the material. A twist bit will have a tendency to grab into the material and want to lift the material, and as it finishes its pass through the material, rather than cut away that little bit at the end, it tends to project out a little lip on the backside, which, if you're looking for a flush fit between things, can be a real a pain to try to address. So we can get around that by using the right thing for creating pilots in that material. So that's going to be hand punching, which we'll show you in a little bit, and or using a step bit. Some of the drivers that I have here are hand drivers, but much of what we're going to be doing with installing tapping screws or sheet metal screws, and most definitely when we're using self-drilling screws, we're always going to be using a power driver of some sort. And so I've got this cordless drill driver set up here that we'll walk you through some of those processes with. So nut drivers come in a lot of different sizes. We have nut drivers that can be hand driven, and these are particularly useful for to do the final tightening of some of these fasteners, especially the more delicate ones where a power driver might tend to strip out the threads that we've cut or tear them away. And we're also going to look at all the different types of drivers that are available for using with a power driver like this. And just because I'm such a tool geek, I had to share this with you. This is a particularly unique screwdriver that I found that has a handle that comes off the side of it to give you additional leverage when you're driving large screws. And that to me is just it's a thing of beauty. So let's talk a little bit about the how we describe these different head styles and what the specific function of those distinct head styles is intended to be used for. Let's take a close look at some of the characteristics of these screws. Let's talk about the materials they're made out of, the types of finishes that they're available in, and those distinct head styles. So our first example here is an example of a Phillips drive flathead that is what's called a binding head, thread cutting, and self-drilling. So self-drilling, self-tapping, binding. This is coated in a epoxy to minimize its resistance to oxidation. Here we have an example of a Phillips drive pan head screw. This is made out of stainless steel. You see the coarse distribution of threads and a drill bit incorporated into the end. Hex head, flanged with a washer, and a rubber gasket or O-ring underneath the head to make a watertight seal. Self-drilling, self-tapping. Hex head, flanged with a washer, self-drilling, self-tapping, and we see them scaling down in size. Here we have a self-drilling, self-tapping Phillips head. And you see the profile on this is very low and very wide. So these are excellent for distributing load over more surface area in softer materials. Here's another example of a similar head and drive style in a shorter length. But this is a simple sheet metal screw that does not have the drilling and tapping capabilities that we saw in its mate there. And as we scale down, you see hex head, Phillips drive, all self-drilling and self-tapping. So different thickness of cross-section will require different size fasteners and different length fasteners. You'll see that typically when you get into the larger sizes of these sheet metal screws, that the heads are, especially if they're self-drilling and are not being used with a pilot, these drills almost always have a hexagonal head because that gives you a lot more positive, secure pressure on the head of the screw to minimize the likelihood of it doing what's called camming out, right? So camming out is, you can see that there's a taper on a Phillips, and if I tried to drive a Phillips with a lot of force, that drill bit has a tendency to hop out of the opening if I'm not exerting enough downward force, or if you don't have the right size Phillips driver. So the hex heads are much less prone to camming out. I think we also have an example here of a here we go, a sheet metal screw that is a proprietary drive system that's called a spanner. And we might be choosing a spanner for its aesthetic properties, but it's most commonly used as what's referred to as a security screws, because the likelihood of your average human having this and being able to remove these sort of limits the likelihood of someone taking these out. And it's not about losing the screws, it's about losing what those screws are holding in place.